Welcome back to CS 520. In this session I'm going to talk about signed integer representation. By representation, of course, I mean what are the bits going to look like in memory at runtime. There's basically three approaches to representing signed integers. One is a sign and a magnitude, another is 1's complement, and the last is 2's complement. We'll look at each one of these in turn. Sign magnitude is probably what you would come up with on your own if you were first thinking about it. And it's the idea of just adding an extra bit on the left that indicates the sign, with a 1 bit indicating negative and a 0 bit indicating positive. So if we think about basic operations on this representation, negate is easy. We just flip that leftmost bit. So let's take a look at an example of that. If I want to represent minus 15, I'm going to start with the binary representation of positive 15. So that's an easy one. And then I'm just going to flip that leftmost bit to make minus 15. Okay, so the negate is easy. But let's consider addition. What if I want to add together 37 to the base 10 plus minus 15 in base 10? I of course should end up with positive 22. So let's take a look. What's 37 in binary? Well, I'll go to hex first. So that would be 2 16s is 32 and a 5. So then in binary I've got 0 0 1 0 and 0 1 0 1. I'm going to be using 8-bit values today, but all these concepts generalize to longer word lengths. Minus 15 I already know, I did it up above. 1 0 0 0 1 2 3 4. So when I go to add these numbers, though, I realize it's complicated, right? I've got to check the sign. If the signs were the same, then I could just add the magnitudes and keep the sign. But if the signs are different, then I have to look at the magnitudes and I have to figure out which one's the smaller, and I have to actually subtract the smaller from the bigger. So in this case, I'm looking at the magnitudes. I got to remember that this leftmost bit is not part of the magnitude. So I'm looking at that, I'm realizing, okay, the bottom number is smaller, so I've got to do a subtract. So let's do a binary subtraction here. Again, when you do these kind of operations, arithmetic, in binary, you really have to go back to grade school and think carefully about how this actually works. So I'm subtracting a 1 from a 1. That's okay. That's a 0. But now I'm subtracting 1 from a 0. So what does that mean? Well, I'm going to borrow 1. All right, giving me 1 0 minus 1 in binary is 1. So that's the case in decimal, where I'm subtracting 5 from 0. I borrow 1, subtract the 5 from the 10 and get a 5. It's the same idea, just in a different base. Okay, I've got a 0 here. I've got to borrow again. And that means I've got to borrow all the way across to here in the left. So now I've got 10 minus 1 is 1, I guess. 1 minus 1 is 0. 1, 0, 0. Let's just check that, make sure I didn't make a mistake there. I've got 16, 6, 16, a 4, and a 2, which is 22. And the sign is the sign of the bigger magnitude, in this case positive. So in fact, I was able to do it correctly. But note, it is complicated, right? I've got to check the sign, and then I have two cases depending on whether it's the same sign or not, and if it's different signs, then I've got to figure out which one is the smaller of the magnitudes, and I've got to subtract. So Subtraction here is fairly complicated. Let's just summarize those thoughts on another slide here. Right, the negate is easy. The addition, though, is complicated. Also note that there's actually two representations of 0. Right? If the magnitude is 0, I can either put a plus sign in front of it, or I can put a minus sign in front of it. So I end up with two representations of 0, which can be problematic because to test for 0, then I've got to look for two different bit patterns. All right, what about 1's complement? One's complement, I'm going to express the absolute value again. But then, if I want to make a negative number, I complement all the bits. And by complement, I mean flip the bits. The 0 becomes a 1, the 1 becomes a 0. So again, let's look at 15. 15 in base 10. Positive 15 is that. And now negative 15 is simply flip all those bits. Those zeros become 1s, these 1s become 0. Okay. So again, the negate is straightforward and can be done fast because we can flip all those bit positions independent of each other, so we can do them all at once. But again, let's consider an addition operation. We do our 37 plus minus 15 again. Again, we should end up with 22 in decimal. 37 again was 25 in hex. Which is 0, 0, 1, 0, 0, 1, 0, 1. Minus 15 I've got up above there in 1's complement form. I want to add these numbers together. And now the rule is it's exactly like adding on side, except if I get a carry out the leftmost bit position. So again, let's work this example. Adding the 1 and the 0 is a 1, adding the 0 and the 0 is a 0, 1 and the 0 is a 1, 0, 0 is 0, 0 and 1 is 1. 1 and 1 is 0, carry a 1. 1, 0, 1 is 0, carry a 1. 1, 0, 1 is 0, and then we get a carry out the left. So when we get a carry out the left, we have to add 1 to the rightmost bit position. So this carry bit comes around here and gets applied. So now we get a 1 and a 1 is a 0, carry a 1, that's a 1, and these bits will be copied down. Okay, and what is that? That is 1, 6 in base 16, which is the expected answer of 22 in base 10. Okay. Let me do one other example just to emphasize that you only add that 1 if there's a carry out the top. Let's look at 10 base 10 plus minus 5 base 10. Of course, we should get 5 base 10. So what's 10? Let's do minus 5 first of all, I guess. To represent that, I've got to represent 5. So 0, 0, 0, 0, 1, 0, 1. Right, then I flip all the bits. So minus 5 would be 1, 1, 1, 1, 1, 0, 1, 0. Okay. So this was plus 5. And then I negated those, didn't negate those bits, I complemented those bits in order to get negative 5. And now let's put 10 on top of that. 10 is 1, 0, 1, 0, 0, 0, 0, 0. Okay, again I'm adding. I'm going to add them just like they were unsigned. 0, 1 and 1 is 0, carry the 1. 1. 1 and 1 is 0, carry the 1. This is not quite the example I wanted, I guess, because I'm going to get a ripple out the top. Have I done something wrong? Let's just double check. Don't think so. So I'll just finish this example. 101 is 0, carry the 1. 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 So again, despite what I was trying to do, I do have a carry out the top. And I've got 0, 0, 0, 0, 0, 1, 0, 1, which is the expected answer. Alright, bear with me. Let's try one more time. I want to come up with an example. Again, like I said, you missed the bottom there a little bit. Let me just show you the bottom answer there, but it came out to be 5. Let me try this one more time. Maybe I should go to a fresh piece of paper. I'm running out of room. Let's try, I think what I probably meant to do was minus 10 base 10. I'm adding that to positive 5 base 10. Why don't we try that? Again, positive 5, well, let's do negative 10. So 0, 0, 0, 0, I've got to do positive 10 first of all. 1, 0, 1, 0, right? That's positive 10. So to complement that, I get 1, 1, 1, 1, 0, 1, 0, 1. Okay, then I'm going to put 5 on top of that. So 0, 1, 0, 1. And of course, there's 0 bits across the top. Okay, so top number is positive 5, bottom number is negative 10. Now I add these together. 1 and 1 is 0, carry the 1. So that's 1, 0, 0 is 1, 1, 1 is 0, carry the 1. 1, 0, 0 is a 1. And now I'm going to get 0, 1 is 1, 0, 1 is 1, 0, 1 is 1, 0, 1 is 1. Note, no carry. So no second addition. This is what I was trying to demonstrate. Now I got a negative result, so let's negate this to see what the magnitude is of this number. So again, 0, 0, 0, 0, 1, 0, 1. When I negate that, it is plus 5. So in fact, this result was minus 5, which is what we expected, right? Minus 5 over here. Okay. All right. So let's take a look at a summary of 1's complement. The negate again is easy and it's fast because we can do all the bits at the same time. But the problem is with the addition. That second addition actually can take just as much time as the original addition. Having to add that carry in a second addition could be just as expensive as as the first addition. Let's take a look at one more example just to try to illustrate that. If I have 102 base 10 plus minus 38 base 10, I should get what? I should get 64, positive 64, right? Alright, so let's represent these numbers. This one is equal to, let's see, gotta do a little arithmetic in my head here. In hex, I guess I want 6 16s because that would be 96, and that would leave 6 for the bottom digit. What about 38? 38 in hex would be 2. That's 2 times 16 is 32, and that would leave 6 for the second digit. Of course, that's a negative number. All right, now we can go to binary. Let's do the 26 first. Positive version is 0, 0, 1, 0, 0, 1, 1, 0. Now I have to, again, this is positive 26. Now I have to complement the bits. 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1. Okay, and now let's put 66 hex on top of that. That's 0, 1, 1, 0, 0, 1, 1, 0. And now again I'm doing addition. Do a little bit more binary addition. 0 and 1 is 1, 1 and 0 is 1, 1 and 0 is 1, 0 and 1 is 1, 0 and 1 is 1, 1 and 0 is 1, 1 and 1 is 0, carry the 1. 1, 0, 1 is 0, carry the 1. So there is a carry bit. I've got to bring it around. And now notice what's going to happen. It's going to ripple all the way across, right? I'm going to get a carry. 1, 1 is 0, carry the 1. 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 1, 0. Okay. And what is that in hex? In hex that is a 4, and that is a 0. So in fact, this is the expected answer of 64. But again, the point here is that the second add can take just as much time as the original add, because that addition of a 1 in the rightmost position, even though it's just being added to the rightmost position, it can ripple across as we get carries out the left. Okay. What else can we say about 1's complement? Well, there's still two representations of 0. Let's take a look at that. 0, 0, 0, 0, 0, 0, 0, 0. Right? That's plus 0, but I complement that and I get minus 0. So again, 2-bit patterns for the value 0, which can be problematic when you're testing for 0, for instance. Note that the sign bit is still the leftmost bit. Again, when we look at that value 15, the leftmost bit is a 0, indicating it's a positive number, really, and when I complement those bits, it becomes a 1. So it's still the case that this bit position is in effect a sign bit, but what's interesting about 1's complement is we go ahead and add that sign bit and manipulate it during arithmetic to get the right answers. What if we had a value that was a positive value that had a 1 in that position? Well, it's too big a value. So the point here is a little bit of a subtle point, I guess, but if this value is positive, that's the magnitude of the number. It is too big to fit in 8 bits. It's too big to fit in 8 bits for a signed right? If the value is signed, then the magnitude can't overflow into that bit. Okay. Why not? Well, let's just complement it, I suppose. If we complement this, okay, it just doesn't make sense, basically. All right. We'll come back to this too big to fit concept in just a minute. Let's look at 2's complement. 2's complement, again, we start out by expressing the absolute value or the magnitude. And if it's negative, we complement the bits and we add 1. So let's take a look at this. Again, let's do 15. So positive 15 is 0, 0, 0, 0, 1, 2, 3, 4, right? Positive 15 minus 15 is now complement all the bits and always add 1. Okay, so 1, 2, 3, 4, 0, 0, 0, 1. Again, maybe I should emphasize here we're always adding 1 now when we negate. Okay. Well, what about addition? Let's go back into our favorite addition. 37 plus a minus 15. Again was 25 in hex, which is 0, 0, 1, 0, 0, 1, 0, 1. And then put the minus 15 and 2's complement underneath it. 0, 0, 0, 1. And what's the algorithm for adding 2's complement numbers? It's exactly the same as unsigned, and just ignore the carry. Ignore any carry that goes out the left end. We're just going to ignore it. So 1 and 1 is 0, carry the 1. 1 and 0 is 1, 0, 0 and 1 is 1, 1, 1 is 0, carry the 1, 1, 0, 1 is 0, carry the 1, 1, 0, 1 is 0, carry the 1. And this time we just ignore it. Okay. And we get back 1, 6 in base 16, which is the expected answer of 22. Okay. So let's what can we say about 2's complement? Well, it's basically a trade-off. The negation now is more complicated, right? I'm going to do that extra operation and bury it in the negation rather than doing it in the addition. So for every negation, I'm going to flip the bits and add 1. Always going to do that. So I'm sort of paying the price during the negation, which makes the addition easy because now I just do the normal unsigned addition algorithm, and if there's a carry, I just throw it away. So makes addition very easy. Doesn't matter whether it's signed or unsigned. I just always do the same algorithm. So basically, we're trading off getting an easier addition at the expense of a more complicated negation. Another interesting side product is we only have one representation of 0. Let's look at 0 and negate it. Right, that's equal to plus 0, but when I try to make negative 0, I flip the bits and I always add 1. And what happens? Well, I get a ripple all the way across So I get 0 right back again. Okay, because this, of course, is ignored. So there's really no plus 0 and minus 0. There's just 0. Okay. That's a nice property. Now I only have one 0-bit pattern to worry about. But of course, if you think about that, that's got to lead to a different problem. For 8 bits or 16 bits or 32 bits or 64 bits or whatever, there's going to be 2 to the 8th bit patterns, or 2 to the 16th, or 2 to the 32nd, or 2 to the 64th, but it's going to be an even number of bit patterns. If I subtract one bit pattern out for 0, that leaves me an odd number of bit patterns to divide between positive and negative numbers. With 2 complement, the extra number, so to speak, is put on the negative side of things. So we're trading off. We only have one representation of 0, but we have one more negative number than positive. And that can also be a problem at times. You forget about it. Let me show you actually what that most negative number is. You might think the most negative number would be this, all the bits set. But if we negate that in 2's complement, we get 0, 0, 0, 0, 0, 0, 0, 0. And now we always add 1 when we're negating. So in fact, bit string of all 1s in 2's complement indicates a value of -1. Okay. Turns out the biggest negative number is this. It's a 1 in the leftmost position and 0s in everything else. We complement that. And we add 1. We get the number back. And again, this is the phenomenon that we refer to as overflow. Right? What this means is, what is this value? This value is this is the 16, 32, 64, 128. Right? That's if we think about it as unsigned for a minute, that is positive 128. Which means this was minus 128. So minus 128 is representable in 8 bits 2's complement. But when I negate it, rather than getting a positive number back, I get the same number back, which means it overflows. I can't represent that number, the negation of minus 128, in 2's complement in 8 bits. If, however, I treat the result as unsigned, then I can see the value as unsigned is 128, which does make sense. But the bottom line is, in an 8-bit container, I can represent the numbers minus 128 and on the right end of the side I can only go to 127. So there's one more negative number than positive numbers. And again, that can cause you trouble. If you forget about that, you negate that biggest value and you expect to get a positive number back, but instead you get overflow and you get the negative number right back as itself, and that can cause bugs in programs. You sort of have to keep that in mind. Okay. A few more thoughts about 2's complement. The leftmost bit still indicates the sign. So again, we sort of saw that a moment ago, right? If the number if the magnitude of the number won't fit in the number of bits we have. I guess this is not a good. Let me start over again. Let's try. What if we look at an 8-bit value, but the magnitude is all ones bits? And again, I flip all those bits. I end up with 1. So I guess there's really not a proof here. It's the reality is that the leftmost bit is still carrying the sign. This value is, if it's unsigned, is too big to fit in 8 bits. Because that leftmost bit will be interpreted as a signed bit in effect, and this value would then, again, we saw this a moment ago, is -1. Okay. So when you're thinking about this, you really have to, again, can I express the magnitude in one less bit? If I can't, the value is too big to fit in the container I'm dealing with. Because if I get a 1 bit from the magnitude in that leftmost bit position, it's going to make the magnitude appear to be negative, which of course doesn't make sense. Okay. But again, an interesting phenomenon, a useful phenomenon, that the leftmost bit in 2's complement still indicates sign, with a 1 meaning a negative number and a 0 in that bit position meaning a positive number. Bottom line is that all modern machines are 2's complement. I guess in the end people were willing to have a more complicated negate at the benefit of having a very easy to implement addition, and they were willing to trade an extra negative number to solve the problem of having two 2-bit patterns for the value 0. So the machines we'll be working with will all be 2's complement. But remember, I think I may have mentioned the CDC 6600 from the 60s that I learned to program first was, in fact, a 1's complement machine. So the world did not settle on 2's complement until, the late 60s, early 70s, I guess. All right, one other thing we should talk about right now is when we're moving values between different size containers. And again, we'll be focused on 2's complement from here on out. So what happens? How do we promote a value from a small container to a large container? So again, if I look at positive 15 and I promote that, the key is it's done via sign extension. Again, that's the sign bit. I'm just going to extend that sign bit across the top if I want to make a 16-bit value. Just going to replicate the sign bit, and that sort of makes intuitive sense, right? I just throw a bunch of zeros on the left end. What about with a negative number, though? If we look at our negative 15 in 2's complement, that was flip all the bits and add 1, right? Well, it's still the same. I'm going to take the sign bit and I'm going to replicate it across the top. So these top 8 bits are going to have a copy of the sign bit, and the bottom 8 bits stay the same. Okay. And does that work? Well, that's minus 15, I claim. Base 10. So let's negate the number. Again, I negate it by flipping all the bits and adding 1. So I end up with, I guess I've written too big, I've got to put my answer over here. I end up with 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4. Right, I get back what I expect. When I negate minus 15, I get plus 15. So again, just remember that when you're going to promote a value from a 2's complement value from a small container to a larger container, you're going to take the sign bit, the leftmost bit in the small container, and replicate that across all the bits of the upper bits of the larger container. What about going the other direction now? Going from a large container to a small container. So let's come up with a different value here. Now let's do 15 first of all, I guess. Again, if I have positive 15, it's pretty trivial, right? I have positive 15 and 16 bits, and I want to move it to an 8-bit container. I'm just going to throw away those upper zeros, right? Just discard them, and that's obviously still the value 15 in the smaller container. And of course it's the same thing if it's negative, right? I've got the negative 15 which is this. If I want to move it to a 8-bit container, again, I'm just going to get rid of those upper 2 bytes. Sorry, upper 2 hex digits. And that, of course, is still minus 15. I just double check that, beat this into the ground, but flip the bits and add 1. I get what I expect, which is 15. Okay, so that's fine. But let's look at when this goes wrong. Right, when this goes wrong, is when I have a value like this. I have 257. Base 10 is going to be right. Again, this is 2, 4, 8, 16, 32, 64, 128, 256, and 1 is 257, right? But now, if I just throw away the upper bits, I obviously don't get, it doesn't work, right? Because now I've got the value 1 rather than the value 257. And this is the phenomenon, again, of overflow. Right, the 257 overflows an 8-bit container. I can't represent the value 257 in a 2's complement 8-bit container. It's too big. How do I know that? Overflow if the chopped bits are not all the same. In this case, I was throwing away zeros, but there was a 1 lurking right there. When I threw that 1 away with the zeros, then I know there's trouble. The result is not going to fit in the smaller container. And this is true of negative numbers too, of course. Let's do minus 257. That's 1, 2, 3, 4, 1, 2, 3, 0, 1, 2, 3, 4, 1, 2, 3, 0, but I'm going to add a 1 because I'm doing 2's complement negate. 2, 3, 4, 1, 2, 3, 0, 2, 3, 4. Right, that's minus 257. And if you're wondering again, maybe I went too quick there, where did this come from? I was complementing these bits up here. Complementing these bits up here, that was this down here, and then I added 1 for minus 257. Now let's move that to a small container. Move this up a little bit. Well, when I discard these bits and those bits, again, I know I'm in trouble because there's a 0 being discarded along with a bunch of 1s. And I end up with the value which is negative in an 8-bit container. I know that that is in fact, right, that is in fact minus 1. So I see the same phenomenon whether the number is positive or negative. When I'm moving a value from a large container to a small container, I'm chopping the upper bits, and if those bits are not all the same, I've got overflow. Right? We're talking about fixed size containers inside computers, so there's going to be values too big to fit in there. And that's going to be something we have to keep our eye on throughout the semester as we do manipulations. Okay, I think I want to stop there with signed representation of integers. The next thing we'll be going to, I guess, will be moving on to floating point, but that will be another session.